Okay, so today we're solving one of the request problem from one of our students. This is a P5 question. This is from October number 19, W1952. Question number 1, it reads, a student is investigating the maximum height reached by a light plastic ball when it is launched vertically from a compressed spring as shown in figure 1.1. So we have initial position, final position, and we're trying to measure the height from center to center. It is said that the maximum height h of the ball and the compression x of the spring are related by the equation 4 pi r cube rho g h by 3 equals to half kx square. Oh, basically mgh equals to half kx square. Okay, the stored energy within the spring equals to the mgh of the whole thing, where r is the radius of the ball, rho is the density of the ball, g is the acceleration of the free fall, and k is the spring constant of the spring. Design a laboratory experiment to test the relation between h and x. Explain how your results could be used to determine a value for rho. You should draw k from h and x. X is the compression of the spring, right? Acha. You should draw a diagram on page 3 showing the arrangement of your equipment in your account. You should pay particular attention to blah 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 blah. Okay, fine. So if you think about it, what are the couple of things that we can think about? First of all, let me just tell you the stuff that comes to my head immediately, and looking for better versions of it later. The first thing is that we want to perform this experiment within a lab environment. So essentially, we should not use too much of a stiff spring, and also we should not use very weak springs like the springs in the pen,
ballpoint pens.
ballpoint pen, the tip column jegula. So we shouldn't use that kind of spring. We have to use a spring that where the coils have in between gaps over here, because we are going to compress that spring. So that's one thing. And also the spring has to be of that kind of a strength. So we have to be choosy about the spring itself first. Second case, we have to have a ball that should be light enough so that it can be shot off from the ground to a significant height, but that height should be the maximum height that we should go for should not be more than the height of the roof, from the ground all the way up to the height of the roof, because that way we have to do the experiment outside our laboratory, which is not very recommended. So, and also we have to make sure that the height that we're going to measure should be vertical height. So the launching process, the spring should launch the ball vertically upwards. So that's also another very crucial thing. We should have a mechanism by which we can ensure that by somehow there should be some sort of mechanism by which we have to make sure that the ball is launched vertically upwards. Then we have to also measure we also have to have a good way to measure the h with good amount of reliability in the sense, what I mean is that we're trying to measure it from h to h. Also, other than doing it from h to h, we can also go for bottom to bottom or top to top. If I was doing this experiment, I would appreciate it to be observing top to top, because whenever we have to use a ball that is actually quite light material, and the density of the ball has to be quite small. And in this case, you can see that they have already used the ball, the formula for the 4/3 pi r cube, which is the volume for the sphere, multiplied by the density of the sphere. So this whole thing gives you the mass of the ball, which means they are assuming that the entire ball is made up with the same material. It's not a hollow ball like a table tennis ball or like basic tennis ball. These are hollow balls which has a material and then inside there is air. This ball should be a solid ball. So what I would think that some of those sponge balls are there which are all made from rubber. They're very squashy. Those kind of balls could be a good choice for this experiment. But one of the obvious implication or complication that we will encounter when we choose those balls is that the moment you're going to be pressing the spring, let's say if you press the spring by a physical mechanism and place the ball on top of it, then the ball would retain its shape. So try to think about it. Let's say we are going to hold the spring at its bottom level by a G clamp on the table. So the very lowest coil is held by a G clamp on the table so that the spring would not be able to go anywhere. And then by some physical mechanism, that can be another G clamp, because by rolling the G clamp, you would be able to screw it down, or that can be some sort of, what can I say? Some sort of wrench mechanism by which you can actually control this thing. But whatever you do, you have to have a achievable and easy to make sort of release device. Release device means that the spring should be in a compressed state that you should do with proper measurement. And you should be able to do that you should do with proper care, so that you can take a good measurement of how much the spring's length has decreased. You should have a good way to measure that. And also you have to hold it in that position for a while, and then let's say on the top of the top coil of the spring we're going to place that ball, so the ball wouldn't be under any compression. And then you have to release the top coil of the spring somewhere over here, and that will shoot the spring upwards. So that's something that is coming to my mind. That's one way to achieve this. The second way that we can achieve, maybe it's also possible that we're going to put the ball on top of the spring, and simply we're going to push the ball altogether. The whole ball will be pushed from the top, and we're going to squash along with the ball. But the problem of that whole thing would be that if the ball is made from a very light material, but it's not perfectly solid. If it's a squashy material like those rubber sponge materials, then the ball will also undergo compression. So you would not have a proper compression stored energy for the spring, because by half kx square it means the compression energy stored within the spring. In that case, your ball will also store some energy which will be unaccounted for. So one of the things is that we should choose a ball. I cannot actually think of that kind of a ball. I mean, that can be essentially made of what? Solid plastic balls. I haven't seen a solid plastic ball, never. Plastic
Billiard balls, sir.
Huh?
Billiard balls, pool balls.
Pool balls could be a good choice.
Aren't they too heavy though, sir?
Well, that depends upon what kind of a spring you choose. I mean, if you choose a pool ball, then you have to go for that kind of a spring. That would be, the ball and the spring, they have to be chosen in pair so that you can actually achieve that experiment. I mean, you cannot use, let's say, have you guys ever seen the spring that is used on the rotating chairs? Have you seen that spring ever? It's quite thick actually.
Yes, sir.
So you cannot use that kind of a spring to launch a ball in a scenario like this. And then again, you cannot use one of those very soft springs. I mean, whatever the ball that you choose and whatever the spring that you choose, they have to match each other's properties so that that experiment can be done within the limited height of the experiment hall. So that's the important thing. So I cannot think of a physical example. A pool ball could be a good example. Or if you don't want to use a pool ball, let's say if you also use a tennis ball, for example, in that case, we have to assume that the whole tennis ball is made up with in true sense, a tennis ball is basically a rubber, the thickness of rubber, and inside there is air. But you can actually measure what is the total volume of the tennis ball, and you can also measure what is the total mass of the tennis ball by using a beam balance. And if you do the division of these two quantities, you're going to get a average density of the tennis ball. Obviously, the border of the tennis ball would be definitely thicker in true sense, and the inside hollow space would have a air within itself, so that would have a much smaller density. But if you can measure the whole thing, if you assume the whole thing to be a uniformly made object, that might serve your purpose. So what I'm going to say, the way I'm going to say that we'll choose a ball that is made of a very light material, plastic, preferably hard plastic. I'm going to mention hard plastic, and it's small enough so that it can be shot into the air for a significant height by a small compression of the spring. So you don't want to use a very light ball that is going to be stick to the roof every single time, even for a small compression of the spring. Then again, you don't want to use a too much of a heavy ball that where the edge gain would be also too small. You cannot use a bowling ball, or you cannot use you shouldn't be use something else.
Ball bearings.
Yeah.
Ball bearings.
Ball bearings would be too small. Yeah, you shouldn't be using ball bearings because ball bearings would be too small for the purpose. So I think for physics, I mean, you don't have to mention what kind of ball you're going to use. You just mention the type of properties that you would use to choose that ball. That's all you have to do. You don't have to give a physical name of the ball. So a golf ball can be a practical example. It can actually work. I think a golf ball can work. Golf balls are also not, to be honest, made of uniform plastic. They also have multiple things within themselves. There is a core and there is everything. So, and golf balls are not are totally made of a single material, as far as I know. Golf ball or the billiard balls, none of the balls that those are used in sport are made of a single material, as far as I know. They have different materials for different type of purposes to be fulfilled. Anyway, the point that I'm trying to make, that we have to choose those two things properly, and then we have to have a way to compress the spring hold the spring in place, and then we have to have a release mechanism that will release the spring, which is going to shoot the ball upwards. And then we have to be able, we have to be we have to make sure that we are measuring the height gained by the ball to that location, and we also have to take in account for possible parallax error. At the same time, we have to make sure that the rise of the ball is remaining unobstructed, and it has to be as vertical as possible. It has to be unobstructed means that, come to think about it, I mean, one of the ways you can essentially make the ball go vertically upwards is that if you set this up in this position. Let me just take this out in the Microsoft whiteboard. I recently found out that I can actually input a whole PDF within Microsoft whiteboard. Isn't that nice?
It's pretty cool.
All right. Okay, I just have to drag it anyway. And here we are. So we're doing this one. So let's zoom in. So one of the things, one of the way, achievable way to make this ball go vertically upwards might be, I'm not saying that this is the only way, but I'm proposing that this might be actually one of the ways. One of the ways that we can achieve that thing might be that we could actually give a guide mechanism over here, a cylindrical hollow guide mechanism, maybe made up of transparent acrylic or transparent plastic, and that would make sure that the ball is actually shot in a straight line. Pretty much, this is basically going to work like the barrel of a gun. The entire purpose of the barrel of a gun is to make sure that the bullet is shot in a straight line in the A direction that you are aiming. If you don't set the barrel, then your bullet could practically go in any direction. That's why a shotgun does not need a long barrel, because shotgun practically doesn't aim anywhere. It actually shoots a bunch of projectiles in a close distance. Shotguns are used for very close shots, not applicable for long distance shots. But if you want to make a long distance shot, you would essentially need a pretty long barrel to make sure that the object is given a good precise a good alignment. So we can use one of those. But one of the problem of using those things is that the moment you're going to shoot this, the ball is going to basically rub off the inside wall of these things, and in that rubbing process is going to definitely lose some energy. Now, if we use a small amount of guiding mechanism to make sure that the ball goes up, and we consider the amount of energy lost within that guide mechanism negligible, or we can somehow lubricate the inside of that guide mechanism for our purpose, that might work. But I'm not sure whether the examiners are going to appreciate that anyway. So the other way that I can prescribe to achieve this can be that we're going to the other way can be that we're going to set. Let me just try to draw a possible diagram of this thing. Let's say this is the space that for our diagram. We're going to draw the table. We're going to show the compressed spring, and over inside the compressed spring, you just represent some sort of a G clamp. It looks weird. You draw something like that, and then draw a nut over here, the handle maybe, and just label this as G clamp. That will work. And then on top of the G clamp, we are going to place the ball, and we're going to squeeze the we're going to squeeze the I have something in my mind, but is it going to work really well?
So I mentioned a launcher mechanism, like you load the spring into a thing, some sort of barrel, and it has a tab on top of it which you pull down. It can launch the ball upwards, kind of like those Hot Wheels launchers.
Actually, to be honest, I mean, here we can actually well, no. This G clamp essentially has an increased head. So normal G clamps are like this, right? Like a oops, no. Normal G clamps are really straight, so it finishes over here. This G clamp is not straight. This G clamp is like this. It has a increased lip. বুঝছো কি বলছি? So you're going to place the lower coil under this slip. So the coil is going to be something like that. Abdul Rahman, bucho? Okay. So that's what I'm proposing. G clamps can come in a lot of different shapes. Maybe you haven't seen this, but I have used this in my university level. So that's why I could call it up from my brain. I'm trying to think of a reliable way to launch this thing and a practical way how we can measure the compression of the spring. I'm trying to think about it. Okay, how about this? How about this? We are going to okay. I'm trying to practically trying to solve the problem. So this is one of those things. This is coming to my mind. Please have a look. Let's say you have a table corner like this. This is the corner of a table. So this is a straight line. Make it straight. Come on. Now they wouldn't make it straight. So let's say this is the corner of a table. So let's say this is the table. This is the break line. So this is the corner of a table. We are going to do this experiment by attaching the spring. So let's say this is the spring. You're going to hold the spring by the G clamp that is placed on this edge, and then you're going to have a piece of lace or tape, not adhesive tape, like normal tape, and you're going to use two more G clamps over here, one over here and one over here, and that lace is going to get stuck at the on these G clamps, and you're going to and that is going to roll up onto the spring, and it's going to go down over here. Do you understand my point? I mean, what I'm trying to show you is that if you look from this side, it might look something like this. So this is the end of the table. So here is the spring. The spring is held in place by one of the G clamps right over here, and there is one G clamp extending on this side, from under which, I mean, there's another G clamp over here like that, from under which there comes out a tape which is going to go on top of this thing, and that's going to be attached with the other end of the G clamp. Do you understand my point? এই ডিজাইনিংটা কি বোঝা যাচ্ছে? Can you visualize this? The reason I'm trying to achieve a tape is that we are going to keep the one end of the tape perfectly in place. We're going to clamp it very tightly, so it's not going to move. And then for the other tape, we're going to pull it by hand. And then we're going to clamp that tape piece over here very strongly. Now on top of this tape, we're going to place a very light piece of cardboard. The reason we're placing the cardboard, because on top of the tape you cannot, on top of this paper tape, you cannot actually place the ball, because the ball is going to be tilted, and essentially if you release the spring, it's going to obviously shot in a random direction. So we're going to place a small piece of cardboard, very lightweight cardboard, on top of this thing, and then on top of this cardboard we're going to place the ball. So we're going to place the ball. So the apparatus is going to be spring, tape, cardboard, ball. And the way we're going to so by pulling this tape in one direction, we can actually make this spring go down a little bit, even by a little bit, and then by attaching this clamp, we can actually keep it at a compressed state. What we're going to do when you are ready to take the experiment, so in this position you can very easily measure what is the vertical height. I mean, you can look from this side and just place let's say you are looking from this side and just place a meter rule over here. So this is the long section, so you just place a meter rule behind it, and by looking you can understand that how much the spring was compressed. You can very well have a look, so you can get a good value of the X the deformation of the the compression of the spring. And then you place the ball over here, and you have to set some video camera. I'll definitely use the video camera over here. You have to set some video camera uh, at approximate heights. So you can set up, let's say, 2 or 3 video cameras, or you can set 2 video cameras at about, let's say, 10 centimeter distance or 5 centimeter distance. I'm using 2 video cameras for one reason. So we're going to shoot the ball, and we're gonna have 1 meter rule over here, 1 meter rule over here, a very long meter rule, which is gonna be referenced from the table as well, and then when we're ready, we're going to cut this tape with a scissor. The moment we're going to cut this scissor, this tape is going to roll down under the cardboard. So the cardboard will basically take the frictional effect of the tape, and the spring is going to extend upwards, and the ball would be basically shot up by the upward motion of the cardboard, and the ball is going to go up pretty much vertically. We're going to, for one specific value of x, we are going to for one specific value of x, we are going to try this couple of times for our best guess. Forget about 2 video cameras. Forget about 2 video cameras. We don't need 2 video cameras. 1 video camera should be more than enough. Let me just erase this. So we're going to for one specific value of x, we're going to give it, let's say, 1 or 2 shots, and have a guess that how high does it go. And we're going to set our video camera approximately at that height in front of the meter rule. And then when you are ready to take the reading, we're going to launch the thing from that same value, measured value of x, and then it is going to go up. And we should try, by trial and error, we should take obviously we're going to take multiple data, but we should definitely try to place the camera in such a place so that the parallax error is as less as possible. To be honest, you cannot avoid parallax error over here, because being able to avoid a parallax error would essentially mean that before even the ball would rise up, you would know how high it's gonna get, and you're gonna place that camera exactly at that position to get a perfectly horizontal view. But that's just demanding that you would know the future, but that's not the case. Experiment,
Sure.
be able to physically perform that. Bolo.
How about keeping the video camera a bit farther away and instead using the slow motion capture?
So we are going to keep the video camera farther away from the ruler and use high definition video, and use the frame view to get the most. Yeah, that can be a very good thing. Yeah, but
And using pixel
very good, because
measurements.
if you keep the video camera quite far away from the ruler, then the angle variation can be considered to be small. So we would know exactly at which point the camera is perfectly loaded. So we would know this thing. So if the moment the ball actually covers this mark, we are going to measure that. Do you get my point? So what I'm saying is that you're setting up the video camera at a height at this position, and this is your meter rule. The ball is going to rise up to this level, and you're going to have a mark over here at the exact level of the আচ্ছা না তা তো হচ্ছে না, আমাদের তো বের করতে হচ্ছে কোন পয়েন্টে সে স্টপ হয়, তাই না? হ্যাঁ, আমরা তো এখানে মার্ক দিয়ে তো আসলে, sorry, forget about that. We cannot actually mark this. We have to be open for the height h. We don't know the predetermined height. In which case we have to do some trial and error to find out the most best position for the video camera height, and place it quite far away from the ruler, so that the effect of parallax error is as least as possible. You cannot avoid this. That's the honest truth. And for every single pair value of x and h, we should repeat the experiment at least 3 to 4 times and take the average of those 2 values.
Sir,
Yes.
let's do it like I mentioned, like pixel calibration, like measurement. Like let the ball make sure that the camera is measuring exactly perpendicular to the ball's trajectory, and when it reaches its apex, you can like use pixel measurement to figure out how high the ball went.
Well, yeah, I totally understand how the pixel measurement works. I mean, what you're proposing is that we are going to have a continuous shot, but within the continuous shot, we are going to only look at very specific part of that whole frame size to find out exactly at what level it is, right? Did I understand you correctly?
slow motion video captures, right? Like
Yeah.
at exact apex, exact highest point, pause and like compare the pixel measurements to the pixel measurements of the ball because you measured R. See, find how many pixels.
That can totally work, but the point that I'm trying to want to impose over here, pixel measurement can give us a very good height for how high the ball is. But here's the deal: let's say for the same value of x, I mean, you have to understand that we're going to cut this string and it's going to slide off. So there are a lot of moving parts, and every single launch, even for the very same x value, let's say within millimeter tolerance, you are not going to get the same height. Which means if you place the camera over here, it is very much possible that for the same value of x, in the first shot it might have jumped over here, in the next shot it might jump right here, and in the next shot it might jump over here. You don't know exactly at which level it's gonna get a perfect jump, because some amount of energy is definitely wasted because of the friction, some amount of energy is wasted because of the non-uniformity of the spring's compression for every single time. Because you have to understand that whenever you are placing the tape over the diameter of the spring, somewhere over here, this is the top view, you cannot always ensure that you are placing it to the exact diameter line of this thing. That's what you're gonna try to do, but being able to do that every single time without fail with appropriate perfection is not possible. So you're not going to have it at every single height. So even for a fixed value of x, which is a control variable, and h is your dependent variable. So a control variable, h is the x is the independent variable, h is the dependent variable. So to measure this h value, if you place your camera at a fixed height, I mean, even though they are going to have a very small variation, you are going to come across some parallax error. You cannot essentially deny this. I mean, maybe for the first reading, you are having a reading, if I go for the top to top, right over here, and then maybe for the second one, you're going to have a height measurement through this line. So let's say it's going to be through this line. So essentially, I actually made it a bit of a curve to make my point, but so let me just, is there a way to draw perfect straight lines, assisted straight lines within this Microsoft whiteboard?
I'm not sure. Sir.
Okay, so let me just try to do this. So let's say this is the straight line that we have. No, actually, let me use red. So let's say this is the straight line that we're gonna that we should have had for the lowest position of the ball. So what you can see over here, obviously, these two positions are going to experience even a slight amount of parallax error. You cannot avoid this because this position is fixed. We're not going to change this position for every single variation within one reading. I mean, if you're trying to get a value of x, you're going to place it at a fixed position and measure all the h for that position. Do you get my point? What you're attempting to do, or what you're trying to do, is to get the most sweet position over here and place the distance in such a way so that your view of the camera is also good, so that you can do the analysis of the data. Also, the parallax error is as less as possible. That's what we can do. Do I make sense?
Yes, sir.
Alternately, much better system could have been, which is obviously not achievable in a A2 level laboratory, is that if we had a motion capture TOR system around this. It's not TOR, there's a name for it. I forgot the name, just a second.
So I got another idea.
Hold up, I'll show you this. I'm going to pause the recording.
That was too real, sir, and yeah, at least I understood the experiment.
Beautiful, beautiful. What was the other similar experiment that you talked about in the first place?
It was like the same thing except with a leaf, a blower, so air blower. It's like
Tell me the year number.
October, November, 1951.
Hmm. Interesting. The H is dependent on the diameter. So if you ask me, one of the control variable, there should be at least two control variable for this experiment. If you ask me, that would be, we should use different balls which are all made from the same material, or they all of them have the same density. That's something that I would very much like to mention. And also, for the entire experiment, the power to the air blower should be kept constant, because we are trying to relate the radius of the ball, which is r, and the height of the ball, which means the power of the air blower should be kept constant. I'm going to mention both of these variables, that the ball, all the balls that we're going to use for this experiment should be made from the same material, and the power of the air blower should be kept constant throughout the experiment. It's a good experiment. It's a nice experiment. There are a lot of places that you can actually show your understanding level. P5 question number 1 is one of those questions where you can actually do some, you have the right to put some sort of, you have some sort of bragging rights in front of the examiners. I mean, like, really show that, yeah, I know my shit.
It's kind of fun, sir, like problem solving.
Yeah, yeah. Some people find it difficult, and basically, if you ask me, beyond the difficulty is the actual joy of achievement. I mean, if you can solve it on your own and actually find out that, oh, yes, at least some part of my thinking was aligned with the mark schemes, or the teachers are appreciating your ideas, even if it's completely out of the mark scheme, that's something that you wouldn't have unless you risk failure.
You can also be creative, sir, which you can't really be in most science.
Yeah, precisely. That's what I said in the first place. That, I mean, this is one of those questions that actually give you some real-time bragging rights in front of the examiner. Like, yeah, I know how to do this thing. That's what I meant. Wow, it automatically centers. Just wow. Okay. So whiteboard has geometric symmetry, but it doesn't help to draw perfectly straight lines. Or does it not? No, it doesn't help to draw perfectly straight lines. But if I draw a rectangle or a square, it will pick it up. No, it is not picking up. What is happening? Goodness. Okay, anyway. Bolo, our problem bolo.
Sir, I had a few questions about like in changes in internal energy and like melting and boiling and stuff and freezing.
Go ahead, ask the question.
Yes, sir. When ice melts, sir, what is happening to the internal energy, sir? Because is potential energy increasing because the molecules are getting more spread apart, and kinetic energy is not increasing because it's a state change. So I'm confused whether internal energy will increase or decrease in that situation.
There are two different answers. There are two different answers for this. Ice is one of those exceptional solid substances available on nature that when it melts, it expands, it compresses. Frozen ice has a bigger volume than the same mass of water. You know that, right? That's why ice floats on water.
Yes, sir.
So unlike most other examples, like metals, most metals, for ice, situation is slightly different. As long as the melting process goes on, both the ice and the water are 0°C. So both the states, molecules of both the states have the same average kinetic energy. The word average is very important. Eta, this information is fixed. This information doesn't have any change. However, if we consider that the average intermolecular force between the particles become loosened up, right? Because in the solid state they were perfectly stuck, and the liquid state they are free to move. I mean, they're not free to
Yes,
move
sir.
like gas, but they are basically not in a
Slip and slide.
yeah, not in a fixed position. Which means, I mean, I can explain this thing in a multiple different set of wording. One of the wording can be that to make the molecules break free from their fixed positions and be able to move around, energy had to be supplied or work had to be done on them to make them free of their structure. The amount of work that had to be done or the amount of energy that had to be supplied to achieve this is going to be stored within these molecules as potential energy, not kinetic. Does it make sense?
So internal energy is increasing because the potential energy is increasing because the separation of molecules
Exactly.
increase.
So yeah, precisely. So one of the ways that you can always get a correct answer, at least a partial correct answer, is that if you think that if you are doing some thermal process, I mean, is this process exothermic or endothermic? I mean, melting an ice is an endothermic process, right?
Yes, sir. It absorbs energy from it, sir.
It absorbs energy, which means essentially the total amount of internal energy will increase. Now, because if you consider the whole thing to be at constant temperature, there is no change in average kinetic energy, which means obviously the potential energy has to increase. Now, this is one part of the explanation. The alternate version is that if we do consider that ice has a bigger volume and water has a smaller volume, which means currently the intermolecular force between the particles got somehow increased because in the ice state they were farther apart, in the liquid state they are closer. Wouldn't that somewhat feel like that closer particles have stronger intermolecular force and farther apart particles have weaker intermolecular force? That's the basic idea that we have come across so far, right?
Yes, sir.
So if we consider that volume decrease information to be a significant factor, if we do consider that volume decrease information to be a significant factor, if we do consider that, in that scenario, in that scenario, we have to say that in the process of volume decrease, the water molecules lost some energy because they are getting closer, which means intermolecular force is working. The force that exists within the object itself, that is working. So whenever any force within the system does work, the total energy of the system gets decreased, right? Whenever external force does work, then the total energy of the system increases. ठीक है ना?
Yes, sir.
So whenever ice is converting into water, the pre-existing intermolecular force is basically pulling all the molecules closer, and that pulling closer thing is essentially responsible to have a decrease in intermolecular decrease in the potential energy or internal energy. But what you have to understand that the amount of decrease that this intermolecular force working to bring the molecules together is going to happen. Let's say the amount of energy lost that happens because of this whole getting closer thing, let's say that is 5 joule, whereas the amount of energy that the whole ice absorbs from the surrounding for achieving the state change, let's say it is 100 joule. So it is going to lose 5 joule from its own because it is getting the particles closer, but it is going to absorb, let's say, 100 joule from the surrounding to achieve the state change, which means ultimately you're going to have an overall energy increase of 95 joule, right?
Yes, sir.
So that is an exceptional case for the ice and water thing. But for other substances, it's much more simpler. For example, if you consider what mm, metal, any metal, whenever any metal melts into its liquid state, it expands. So expansion means that intermolecular force was somewhat loosened up. So external energy was responsible to make that increased gap. Increased gap means more potential energy. So that actually in that case there is no reduction of potential energy because of getting closer. There is increase of potential energy because of increase in intermolecular distance, and there is also increase of potential difference, potential energy, increase of potential energy because of weakening of the intermolecular force. So both of these factors for a solid metal into liquid metal, both of these factors practically attribute towards a positive increase of potential energy. But for ice, the volume change attributes towards a reduction of potential energy, whereas the intermolecular force weakening causes for a increase in potential energy. However, that increase is always significantly bigger than the decrease of the volume factor. কম্পারিজনটা কি বুঝা গেছে?
So ice is just an exceptional case, sir.
Ice is a very exceptional case, yes. But এই যে এতক্ষণ যে গুলো করলাম, all of these discussions are only viable or only relevant if, according to the question, the volume change for the ice to water is considered to be a significant factor. If they consider that it is not a significant factor, if you wonder that why should it they consider it not to be a significant factor, because here's the deal: in a solid substances, particles, they are basically touching each other, but they are not moving around. In a liquid substance, particles are still touching each other, but they are moving around. So if you come to think about, let's say, you try to visualize, let's say you have some marbles, and if you put them in a jar and they are practically touching each other, you have some intermolecular gap. If you roll the jar, the marbles are going to roll over, which basically represents somewhat like a liquid. Now let's say if you keep the jar vertical and put some glue within those marbles, it's going to cover all the in-between space, and after some time, the glue is going to become frozen, and the whole thing will become a chunk of marble solid piece. You do understand that even in this case, the marbles are practically touching each other. The intermolecular distance hasn't changed. That's also a very close representation for what happens whenever substances change from solid to liquid. You do not have fixed position, but particles are still pretty much touching each other. So there is very less increase or very less change, increase or decrease of intermolecular distance whenever solid converts into liquid, which happens to be a very large thing when liquids convert into gas. That's like a totally mammoth expansion. Make sense?
Thank you for the marble analogy, sir. It opened my third eye. I can find. I understand now.
Yep. Sure, no problem. Arzu?
Yes, sir. Just like like MRI, precession of nuclei. What does that? So we're starting NMR in like chemistry, and we didn't really talk about like the precession thing, but in physics, the MRI thing, it
Yes.
talks about precession and how it absorbs radio frequencies. The radio frequency is released. I don't really get how it's different from spin.
You don't get how it is different from the spin.
Yeah, how it's different from spin and like.
Okay. First of all, hands down, I am not a specialist on this. I just know the amount that I am supposed to know to be able to teach you. So that's disclaimer, like star mark, short প্রযোজ্য. So I am not an expert on this. So I'm gonna tell you stuffs that I do know for a fact are true and relevant to your syllabus. So if you ask me deep level questions, I might not be, or I will not be able to answer those. But hear me out. Certain atoms, nuclei, certain elements nuclei has a property called spin. In an untreated material or in a naturally occurring specimen, all the nuclei has random axis of spin, random axis, or their spins are all different. If we want to use this spin property for some sort of diagnosis, or if we want to use this spin property to be able to detect those position of those nuclei, we have to somehow make them emit some sort of electromagnetic waves so that we can find out precisely where they are. এই পর্যন্ত বুঝা গেছে কিনা?
Yes, sir.
Okay. So the way we make sure of this is that whenever we apply a very strong magnetic field, that first of all brings all of those spinning nuclei having a same axis, like a perfectly same axis. So in that case, all of their rotational axis becomes parallel to each other. So they would all have the same parallel axis. Then at that point, all of their rotating frequency, or something that we call the what is the name of the scientist? Forgot the কি যেন নাম, এটাকে যেন কি ফ্রিকোয়েন্সি বলে?
Larmor.
Lamar frequency, exactly, ভুলে গেছিলাম, হ্যাঁ। So that the frequency of that rotation is of all of those nuclei which are now have the same axis of rotation, they have the same Lamar frequency, which means basically the frequency of spin. This behavior that all of them have the same axis of rotation is called precession. As this combined behavior of all the nuclei having the same axis of rotation and thus having a
Sir?
single value of, yes,
সে কি কাঁদতেছে?
আমার পিচি আমার কোলে, আর আম্মু ওয়াশরুমে গেছে ওই জন্য।
ও স্যার, ওর নাম কি?
ফাতিমা। আম্মু 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 আম্মু
স্যার ওর কত মাস? মানে
6 শেষ হয়েছে, 7 চলতেছে,
ও
এবং সে কন্টিনিউয়াসলি আমার মাইক্রোফোনে তার ধরতেছে এবং তার হাত থেকে ছাড়া দিচ্ছি বলে সে কানাকাটি করতেছে। আচ্ছা যাও, আমি বলে শেষ করি। আবিয়াজ,
Yes, sir.
সো শুনো, সেটা হচ্ছে this behavior or of all the nuclei to have their spin axis parallel to each other is called precession. And at this stage, because all of them have the same frequency and they're all affected by the same value of magnetic field, strong magnetic field, all of their spin frequency, something that is that we define as the Lamar frequency, is also same. Precision জিনিসটা কি বুঝা গেছে? যেমন আমি তোমাকে একটা ফিজিক্যাল এক্সাম্পল দিই, মনে করো হচ্ছে একটা মাঠে একটা আর্মির লোকজনরা দৌড়াদৌড়ি করতেছে, ওকে, then we blow the whistle, everyone stops at their position, then we blow a second time, everyone comes down and get in perfect lines with exactly equal distance apart from each other, right? That happens. Those two whistle blows make them into perfect or arrangement. Precession is something like that. Before blowing the whistle, before the magnetic field is applied, all the nuclei have random direction of their axis, spin axis. The moment you apply that strong magnetic field, something like the whistle, all of these nuclei now have a fixed orientation of their axis. Spin axis is changed. So in this orientation or having to achieve this whole uniformity of all the nuclei in their spin behavior is what we call precession.
And the energy emitted from that is there will give
No,
us.
I haven't yet come to that part of energy. I up till now I have only defined what the precision is. Etu বুঝছো কিনা?
Yes, sir. The alignment of the nuclei in the same direction.
Exactly, the element of the axis of the spin axis of the nuclei. Now at this point, all of those nuclei has the same Lamar frequency. Now the way we were going to detect these elements, or the way we're going to detect this nuclei, is that we're going to feed these nuclei some electromagnetic wave / photons of the same frequency of the Lamar frequency, which these nuclei are going to absorb. And then we're going to stop feeding them this energy, and the nuclei would take some time from the point of stopping the energy supply. These nuclei are going to take some time to come back to their original state. So I mean, let's say the Lamar frequency of all of these nuclei are currently let's say 10 hertz. I'm just choosing number. So if you send some electromagnetic waves of 10 hertz frequency towards this nuclei, They're going to absorb that energy because that perfectly matches with the frequency, and they're going to store that energy. This is what we call the excited stage. Let's say you stop the energy flow. Let's say you stop the 10 hertz energy flow and electromagnetic wave. The nuclei are going to stop the energy receiving, obviously, because you cut off the supply, but they are not going to come back to their original energy level, or they're not going to emit out that absorbed energy immediately. They're going to take some significant amount of time before they emit out that amount of energy. And that time plays a very important role for the MRI scan process. How much time is required for the nuclei to come back to their original energy level or original energy state, or we call it de-excitation. How much time is required for the de-excitation process? That amount of time is an important factor for the MRI process. Now, how that time is important, it was not discussed in your syllabus, and I didn't study about it. I cannot tell you this. I can only tell you that this time is important. Etu বন্ধু বুঝছো?
Yes, sir.
So এটা হচ্ছে আরেকটা part. There is another part is that after when the nuclei are become de-excited, they are going to emit that exact frequency of electromagnetic waves from those nuclei. And by placing an appropriate detector, we can find out from which locations of the patient's body those electromagnetic waves of 10 hertz value are coming out. And those locations would represent the location of those nuclei, which means the location of the element. And that's how we do that scan process. So here's the deal. I mean, if I go through this whole section one more time, is that first we apply a strong magnetic field where all of those nuclei has the same precision and they have the same Lamar frequency. Then we can feed. I'm not saying we will. I'm saying then if we feed all of these nuclei a single value of electromagnetic wave, which has the same value as their Lamar frequency, which happens to fall in the radio frequency range. I mean, we didn't ask those elements to choose radio frequency. The Lamar frequency of hydrogen nuclei happen to fall within the radio frequency range of the electromagnetic spectrum. বুঝছো কি?
Yes, sir. By coincidence.
Yeah, by coincidence. It's a thing that the nature fixed. So, but to be honest, we can slightly control that Lamar frequency by controlling the strength of the magnetic field by which they are affected. So they have a basic value around that thing, but there can be slight variation. For example, let's say in the Earth, most of the people have an average height, but there are people in certain communities of the Earth where all the people are very tall, and there are certain communities in the world where all the people are very short. Now, that's just two extreme values, right? So what I'm trying to tell you is that the basic the gross value of the Lamar frequency of hydrogen nuclei happens to fall in the radio frequency range. So, but we can slightly change those Lamar frequencies by controlling the magnetic field which we applied to make them to give them the precession movement. So change of the magnetic field strength is also a key factor for us to get different Lamar frequency for different nuclei. Now you might wonder, why is that important? Here's the deal. If we apply a strong magnetic field within a patient's body, all of those hydrogen nuclei will have the same Lamar frequency. If we feed those nuclei, or if we send that same value of Lamar frequency into the patient's body, radio frequency wave into the patient's body, all of those nuclei will become excited, and they will all get de-excited at the same time because they all have the same Lamar frequency and they're all the same element. And practically we'll see all the position of those hydrogen nuclei all over that patient's body. That is not diagnosis. That is going to be a huge amount of data, which is not very useful. The way this data can be made into useful, if we can get this radiation radio wave out, the de-excitation for a very specific group of nuclei which we want to excite and de-excite. If you could somehow pinpoint, or if we could somehow excite and de-excite a very specific location of the patient's body and have that energy absorption and giving up by those specific nuclei, then that would be a diagnosis, being able to do a very precise thing. How can we do this? Here comes the idea of the non-uniform magnetic field. So what do we do? That first we apply a strong magnetic field into the patient's body. As a result, all of those nuclei become precessed with the same Lamar frequency. Then we apply a non-uniform magnetic field to the patient's body. Now, because magnetic field strength is a vector quantity, depending upon the value and the direction of the magnetic field strength produced by the non-uniform magnetic field, getting vector summed with the strong uniform magnetic field across individual cross-sectional section of the patient's body, we can get hydrogen nuclei undergoing precession with different Lamar frequency values. But it is always designed in such a way that one single slice of the patient, let's say pet barabar একটা slice through the belly, one single slice of the patient's body, all of those hydrogen nuclei currently existing at that slice, they will have the same Lamar frequency. 1 millimeter down, they're going to have slightly different. 1 millimeter down, they're going to have even slightly different. So you can basically gradually change. You can have a gradual variation of the Lamar frequency of all of those hydrogen nuclei by introducing a non-uniform magnetic field. এই পার্টটুকু বুঝছো কিনা?
Yes, sir.
Okay, so we do that. Once we do that, then we have different values of Lamar frequency across different sections of the patient's body. Now the part of the picture that we want to do, the part of the patient's body that we really want to diagnose, we're going to send a radio frequency that is exactly matching with that slice's Lamar frequency. Let's say we want to take an MRI of a patient's torso right underneath the last rib, the very last rib, at that plane through the cross section of the patient's body. We want to take an MRI picture. So let's say at that layer, the Lamar frequency of those hydrogen nuclei is, let's say, 16.5 hertz. Let's say. So we're going to now send a radio frequency of 16.5 hertz to the entire patient's body. Because this frequency is only matching with those specific nuclei, these radio waves or these radio photons will be only absorbed by those nuclei exclusively. Other nuclei would not even absorb this energy. They are simply going to let it go. This is somewhat similar to resonance, that if you provide a physical vibration, an external vibration to an object with a frequency equal to its natural frequency, only then you can get it to move very with a high amplitude, right? But if that external frequency, external source applied frequency is somewhat mismatching than the natural frequency of the object, you cannot achieve resonance, right?
Yes, sir.
So that's essentially what we're doing. We are sending a very exact value of radio waves to that entire patient's body that matches with a very specific section of hydrogen nuclei, and that causes those nuclei to become excited. Or we use this term because we are causing a very few elements, few nuclei.
Sir, আজকে I don't know enough.
আমি তোমাকে পরে আবার এখান থেকে বাকিটুকু বলবো না. It's impossible to read the class right now. Allah Hafiz.
Okay, sir. Allah Hafiz.